So welcome back for the third module of this week. So in the last module we had finished the discussions on hidden Markov models. How do we learn the parameters and how do we use that for estimating the part of speech text sequences for a given sentence. Now hidden Markov models were generative models, okay, and if you remember we discussed this distinction between generative model and discriminative model. So we will see a discriminative model, maximum entropy model, for this sequence labeling task. But before that, let me start with some sort of motivation on why do we move from HMMs to maximum entropy model. What are the limitations of HMM? So one problem with the HMMs, also this is known as the Markov model tagging, is handling unknown words. Suppose at runtime you get some unknown word that was not there in the corpus, because the emission probabilities will not be known, there is no way you can actually use the Viterbi decoding. So what do you do in that case? So you might want to use some sort of morphological cues. Okay, suppose the word is ending with ed. You might think that this might be a past tense of a verb that we did not encounter in the corpus. Or suppose you are finding capitalization in the middle of the sentence. You might think that this might be a proper name. But how do you actually include that in hidden Markov models? Second, so we use the first order Markov assumption where each tag depended on the previous, only on the previous tag. So this does not take care of certain situations. For example, here I have two sentences, it clearly marked versus he clearly marked. So what you are seeing here, marked in one case is a past participle in the first case, second case it is a verb in past tense. But just the previous context is not sufficient to tell this. Okay, so because in HMMs we are only using the previous context, this might not be sufficient to handle this particular case. So how will you take care of this issue? So you might want to move to a higher order HMM, say second order. Okay, so you can use a higher order model. But this is just some limitations. Suppose you want to use whether this is the first word in the sentence, okay, or you want to use any arbitrary thing like whether there is a verb ending with ed previous to this word. You want to use this information. There is no way you can use that in the case of HMMs. So that's where we move from HMMs to maximum entropy model that allow very heterogeneous set of features. So you can use a lot of different observations from the data for your model. So what is the important distinction? So now in the maximum entropy model, so they are discriminative as compared to generative models which are HMMs. You are allowed to identify a very heterogeneous set of features, not only the tag given the previous tag or the word given the tag. You can use any sort of features which you think might contribute to the choice of part of speech tags. Okay, so for example, whether this is the first word of the article, this is something that you can use as a feature in maximum entropy model. Or whether the next word is TO, you can use the next word as a feature. Whether one of the previous five words is a preposition, this is again something that you can use as a feature in maximum entropy model, but your HMM cannot make use of this. So what maxent model does, it combines all these various heterogeneous features in a probabilistic framework, okay, to be able to come up with the actual part of speech tag sequence for a given sentence. So this is the maximum entropy model. So this is how you write the probability of, so y is the class that is one of the probability for any of the tags, given x is my observation. It can include anything in my context. It can include the current word, previous word, next word, anything in the sentence. Okay, you can define your context while you are dealing with maximum entropy modeling. You are saying that I can use all this information in my features. Given this, I want to compute the probability of my class. And these are discriminative models, so I can directly compute the probability of class given the observation. Okay, so I can compute y given x. And how do I compute that? It's written simply as, it's a log linear model, so summation over lambda I and fi xy. Now fi xy are my various features that I have identified over my observation x and my class y, and lambda I are the weight given to the feature fi. So each feature fi is given a weight lambda I. So I sum over all the possible lambda I fi's and take an exponent, and then I do some sort of normalization, so that probability y given x adds up to 1 for all the possible class h y. Okay, so this is the normalization constant. So it's a very simple form of maximum entropy model. So let me tell again. So z x condition on the parameters lambda is a normalization constant. So this is nothing but this exponent you sum over all the possible class h y. Okay, for all the possible class h y you compute this and add this. So once you do that, you are ensuring that probability y given x will add up to 1 for all possible y's. And lambdas are my features, the weights given to my different features. Now x denotes my observed data, and y denotes my class. Now what is interesting is that what is the form that the features in maximum entropy model can take, as opposed to something like a HMM. What are the features? So what is interesting here, you are seeing f is a function of x and y, both my observation and the class. So I am defining my feature on both of this, and these are all binary features. So let us see what are my features. So in maximum entropy model, my features encode elements from the context x and the tag y. Now context x is, now this is something that you must be careful about. Context x is not my current word w, but is taken around the word w. Okay, I can define my context. It can be the sentence that contains w. It can be its previous 3 words, next 3 words. It is something that can be defined on the current word. Okay, and y is the tag that I am predicting. Now what are my features? These are binary valued functions over x and y, and this is like fxy is 1 if a certain condition hold on x and y and 0 otherwise. And here is one example of what can be some conditions, like I am having the current word w. If the word w is capitalized and my tag y is nnp, then my feature fxy will take a value of 1, otherwise it will take a value of 0. That is one sort of feature. Okay. Similarly, you can define any arbitrary set of features that we have said. So it can be fxy is equal to 1 if one of the previous 5 words has a tag of preposition and the current tag is say verb. This is one sort of feature, 0 otherwise. So like that you can define, and so you have a lot of freedom here in defining and choosing your features. And once you have computed all these features, the model learns the weights for all these features, the weights lambda, and then there is very simple function to compute the probability of class given any observation. Okay. So let's see some other examples for the features. Okay. So this is again for any generic sequence labeling task. So here it is for finding named entities. So it can be here like location, drug and person, 3 different named entities. And some examples are given, like in Arcadia is a location, in Quebec, location, taking Genentech is drug, and Saussure is a person. And now you are defining certain features. So let us see certain features, like the first feature is my tag is location, so my class y is location, previous word that is on x, previous word is in, and my current word is capitalized. So what are all the cases where this feature will be 1? It will be 1 here in Arcadia, previous word is in and it is capitalized and the tag is location. It will also be 1 for second case. Yes, capitalized, previous origin, and the tag is location. Next feature. So why is location and W has an extended Latin character? So you can see that you are using a very arbitrary set of features. Okay, but possibly you have some hypothesis that these features will be helpful for this task of predicting the tag for this word. So this is this feature. So for which of the case it will be 1? It will be 1 for the second case. It has an extended Latin character. Okay, and the tag is location. Third feature, Y is a drug and the word ends with C, and there will be 1 for taking Genentech. Yes, the word W ends with a C. So you can see some examples of what kind of features you can take. But important thing is to know the intuition that you can choose any feature around the word W, and that involves also the current class. So how do we, so now once I have all these features, suppose the learning has taken place, I know all the parameters, lambdas, how do I go about tagging my sentence with the tags? So I have the words in my corpus W1 to Wn, and I want to find out the tags, the optimal tags. So what I will do, I want to find out the tag sequence T1 to Tn. So any sequence will have this conditional probability, right? So Ti conditioned on Xi for I is equal to 1 to n. Now this is Xi, not Wi. Xi is my context around the word Wi, and this is independent. So I can use this model to find out what is the optimal tag sequence. I can do it independently for each word, and then I will find out tag sequence. Okay. So as we have said, my context Xi may also include some previously assigned tags for a fixed history, and I will be using a beam search algorithm for finding the optimal or the most probable sequence. So this is something we will take up in the next lecture in detail, that how do we actually go about doing beam search in maximum entropy model. So yeah, just a brief idea here. In beam search what you do actually, so you have positions in the sentence starting from 1 to the end. So at each position you will keep only the top k possible sequences, and next time starting from these k complete sequences, you will find out what are the next k best sequences. Okay. So let me just quickly say, so I have from, suppose my sentence has n words. So what is the idea? Suppose my beam size is k. So at point 1 I will keep top k sequences. So at point 1 I will have only one part of speech tag. So that means I will keep top k part of speech tags at this position 1. Now when I go to position 2, now I will have a sequence. Now 2 might have some other possibilities of part of speech tags. So what I will do, I will find out the probability of each of these k with all possible part of speech tags here, and store top k sequences again. Okay. So tag 1, tag 2, some case top k sequences. Again at 3 I will have some possibilities, top k times these possibilities, again store only top k out of those, and you keep on doing that until you are here. So here you will choose the best one, and that will give you the complete sequence. So important here is that at each point you are storing top k full sequences starting from the initial point. So here you will find some T1, T2, here you will find some T1, T2, T3, and so on, top k at each time. So we will look at this in detail in the next lecture. So for now, let us look at the basics of maximum entropy model. So what is a maximum entropy model? So maximum entropy model has this particular principle, that is, you are given the observation and you have certain hypothesis. So you take what is given to you, but do not make any additional assumptions. So, that is, take the model that satisfies all the constraints that you are having, but does not take any other assumptions. Okay. So what does that mean? So, you are given a collection of facts, yes, and you want to take a model that is satisfying all these facts, or you are saying that is consistent with all these facts, but otherwise it is not making any further assumption. That is, after satisfying all these constraints, it is as uniform as possible. Or in other words, for all the possible models that satisfy a given set of constraints, choose the one that is the most uniform of all. Now, what do I mean by this? Let's take a simple example. So, here I have a simple example. I have an English word in, and I want to make some translation system that tries to mimic some, so it is translating from English to French, okay, and I have some data already with me from some actual translator who translated some sentences from English to French. Now, so I want to model this expert translator's decision, that how do I translate this word in to any French word. Now, how do I start? So suppose you have a vocabulary of all possible French phrases, okay, and you want to estimate probability PF. So that is, what is the probability that that French phrase will be a translation of the English word in. So you want to compute that for all the possible French phrases. There might be, say, millions of French phrases. So what you will do, you will start by collecting a large sample of instances of expert decisions. Okay. Now, from this facts, you will try, from this sample you will try to observe some facts. For example, so the goal would be extract some facts from the sample of instances and then use these facts inside your model. Okay. So firstly you have to extract the facts. So in our scenario, this will be equivalent to finding out the features, that is my facts. And once I found these features or the facts, I use them directly in my model. So let us see what are the different sort of facts I can find out. For example, this can be my first clue. So I find that in all the samples I have seen, the translator always translates in into one of these 5 phrases, like the, akude and pada. So there are 5 different French phrases where the translator is translating. So now this is helpful to explain what is my maximum entropy model. Now I want to find out the probability distribution over French phrases. All, so suppose I have say 1 million French phrases. So F1 to F million. Okay. So I have 1 million French phrases. I want to compute this probability distribution. I want to find out this probability distribution. Given this constraint, that is, the translator always chooses from one of these 5 phrases. So what is my constraint? This would be, so let me call these F1, F2, F3, F4, or say so let me call these probability, say F1 plus probability F2 plus probability F3 plus probability F4 plus probability F5 is equal to 1. So this is my constraint. Now, so now, given this constraint, I have to choose one model. So suppose I have only this much information from the data. Now what is the model that I should choose among all the possibilities? Now firstly, do you think there are infinite number of possibilities in which I can choose my model that satisfy this constraint? So of course, probability for F6 to probability F million will be 0, okay, because if any of this is non-zero, this constraint will not be satisfied. Yes. So because all the probabilities need to add up to 1. So that means all these are 0. This is anyways easy. But what are all the models that will satisfy this constraint? So you can see there are infinite solutions for this equation. So you can choose Pf1 any number from 0 to 1, and you can always find some f2, f3, f4, f5 that will satisfy, and same goes for f2 and so on. So there are infinite models that satisfy this constraint. Now what maximum entropy model does, among all the models that satisfy this constraint, it takes the one that is most uniform. Now among all these models, what is the most uniform model? So that is, you are not making any other assumptions. Given this constraint, take the model that is most uniform. So it is easy to see in this case that the most uniform model will be one that gives Pfi is equal to 1 by 5 for I is equal to 1 to 5. Okay? For all these 5 phrases, it gives the probability 1 by 5, and everything else, it gives the probability 0. So this is the most uniform model given this constraint. Yes? So allocate the total probability evenly among all these 5 phrases. That is the most uniform model subject to our knowledge. Now, is this the most uniform model overall? Suppose I didn't have this constraint. What was the most uniform model as such? The most uniform model will be that gives equal probability to each of the million French phrases. So it gives a probability of 1 by million to each of these. That is the most uniform model. So the model that I have obtained, which is giving probability 1 by 5 to each of these 5, it's not the most uniform model. It is most uniform given this constraint. Okay? Given this constraint, this is the most uniform model. And this is the idea. So I will take some facts, some observations. Given the observations, I will find out what is the most uniform model. Let's go further. So this was easy in this case. So where we had 5 phrases only. Now so I got a second clue that the expert chose either the or a 30% of the time. Okay. So they were suppose F1 and F2. So now I have, so this is my constraint 1. So now I have constraint 2. Pf1 plus Pf2 is equal to 0.3. Now given these two constraints, what will be the most uniform model? So if you just take a quick look, you can see that the most uniform model will be Pf1 is equal to 0.15, Pf2 is equal to 0.15, and F3, F5 each will get 0.7 divided by 3. And that will satisfy both the constraint. This will be the most uniform model. Okay. So this is not as uniform as this model. So as you are getting more and more observations, you are going far from the most uniform models. But you are coming up with some other models that are as uniform as possible, but satisfying these constraints. Now what happens if you get a third clue? Like in half of the cases, experts chose either the or a. So that is Pf2 plus Pf3 is equal to 0.5. That is 3. And now immediately you will see that it becomes difficult to just look at this equation and try to solve for what is the distribution that is most uniform. And that's where we will need to understand the concept of maximum entropy. So I want to find out the model that is most uniform given the constraints, and that is equivalent to finding the model that is having the maximum entropy among all. Okay. So now, so yes, how do we, so as we get more and more clues, it becomes difficult to see which is the most uniform model. So for that we have to understand how do we measure the uniformity of a model, and that's where we use the idea of entropy. So some of you might have already come across this term of entropy. So what is entropy? Entropy measures what is the uncertainty of a distribution. So going to the basics. So suppose I have an event x that occurs with a probability of px. Okay. So entropy measures what is the amount of surprise in this event. So if it is very, very surprising, then the entropy will be high. If it is like very obvious, the entropy will be low. So for an event, when it is more surprising, when the probability is low, probability is high. When the probability high, it is like obvious. Okay, so then the entropy will be low. But when the probability, so the entropy will be low. But when the probability is low, so there is a lot of surprise in that event if that happens. So then the entropy is high. So that's why entropy is log of 1 by probability. Okay, so the probability is low, entropy will be high. So for a distribution, how do we compute the entropy for a distribution? So I just take the expected value of surprise, that is summation over px log 1 by px. Okay. So I take the expected surprise over all the possible values of p. So this is a very, very standard formula for entropy, minus summation px log px. Now, so here we are talking about distributions. In the case of distributions, when will be the entropy maximum? So if you look at this formula, so let's take one simple example of coin tossing. Okay, so I'm tossing a coin, so it can be head or tail. Let us say that head has a probability of p and tail has a probability of 1 minus p. Okay, so what is the entropy of this model? It will be minus p log p minus 1 minus p log 1 minus p. And if you actually, so these are all based on 2. If you actually go on plotting this as a function of p from 0 to 1, you will find that the entropy starts increasing, it becomes the highest at p is equal to half, and it starts decreasing afterwards. Now can we intuitively understand this? So what we are saying, when both head and tail have equal probability, then the entropy of my model is the highest. What is entropy? It measures how much is the surprise. Okay, so let's take a point like this. So at this point, what will happen? So head has a probability, very low probability, but tail has a very high probability. So you more or less know, okay, it will probably be tail. When you toss a coin, it will probably, most probably be a tail. So there is not much surprises that are coming. But when both head and tail have equal probability, then you are very, very confused. You do not know whether it will be head or it will be tail. So the amount of expected surprise that you will get is the maximum. Okay, so this is the idea. So this is a distribution over only this two variables p and this p and q, or you can say this have p and 1 minus p. But even if you take any n number of variables, the distribution will be having the maximum entropy whenever it is the most uniform. Okay, so this gives us the intuition that why we chose the most uniform model for getting the maximum entropy. Now, coming back to our maximum entropy model. So we want to, among all the possible distributions, we want to choose a model that maximizes my entropy. Okay. Now, so I want to maximize my entropy subject to certain constraints, right? So we will have certain constraints from the data, and these constraints are nothing but my features. So I'll select some features, and I'll make sure that the empirical probability from the data that I'm finding for the features is similar to the probability that my model is giving that. And subject to this constraint, I will maximize my entropy. As you have also seen, as we keep on adding constraints one by one, the entropy of my model decreases. Okay, it comes close to my data. Initially, you might start with the most uniform model that is giving the equal probability to everything. But as you keep on adding constraints one by one, you come you go far away from the most uniform model, so you decrease your entropy, and you come closer to data. So this is the idea. So given some constraints, we want to come as close as possible to the data, but otherwise we want to obtain the most uniform model in terms of maximum entropy. So coming close to the data in this case means finding the empirical probabilities of these features and trying the model probabilities to be close to this. So this is my maximum entropy principle. I am given some n different feature functions f1 to fn. I want my probability distribution P to lie in the subset of all the possible distributions that satisfy this constraint. Okay, so all the probability distributions that satisfy this constraint, among those I want to choose the one that is having the maximum entropy. Okay, so what do I mean by satisfying this constraint? So what is the empirical count of or expectation of a feature? So empirical expectation is how many times this features actually this xy actually occurred and fi xy was 1 in my data. Okay, so p hat is my empirical probability. Now what will be my model probability? So it will be, so model probability Pfi will be summation xy pxy fxy. Now this pxy, because we are computing finally py given x, I can write as summation xy px py given x fxy. Okay, and because we are not computing px in our model, I can probably approximate it with the empirical count of x. So this gives me the model probability of the feature. So I want to make it closer to the p tilde fi. That is the empirical probability of the feature. Okay. So I have the empirical count, model count, and I want to select the distribution that is most uniform subject to this constraint. Okay. So now, so I am computing this probability distribution. So what will be the maximum entropy model? That is the one that gives me the highest entropy hy given x, and that if you do some quick maths, that will be minus sigma xy px py given x log py given x. Okay, and again we will approximate this by p tilde. Okay, so this is my maximum entropy model, and I want to maximize it subject to constraint that this and this are equal. So this gives me the model, maximize this h subject to these constraints. Okay, so for that we use the trick of doing the Lagrangian. Okay, so I want to now take a Lagrangian P-O lambda, that is my h p plus summation I lambda I p fi minus p tilde fi. So that is, I want to maximize this, sorry, so I want to maximize this, yes, subject to this constraint. Okay. So now, if I put these values inside this, so I will get plus sigma lambda I summation xy pxy, that was p tilde x Py given x fxy minus summation xy p tilde x y fxy. Okay, this is my Lagrangian, and I want to maximize that. So I want to find out this distribution that maximizes this. So let me just substitute this with t everywhere. Okay, so in turn what you are doing, you are maximizing it with respect to this t, and that you can do by differentiating it with respect to t. Okay, and then putting it to 0, and that will actually give you the equation that we have seen, that is p lambda y given x, that is our t in this case. It will come out to be exponential over summation lambda I fi xy divided by the normalization constant. Okay, this is a simple exercise that you can do. You can just differentiate it with respect to this parameter t, and you will actually come up with something close to what we have seen in the formulation of maximum entropy model. And this normalization constant is nothing but something that makes this probability p lambda y given x summation over y to 1, and that gives me the normalization constant. Okay, so this is my maximum entropy model. So you have to, the important part here is to find out the set of features. Once you have the set of features, you can use this particular equation to compute the probability of a class y given the observation x. So next, in the next lecture, I will try to take up is a problem that will make the idea of maximum entropy model further clear. Then we will see how, given a new sentence, we use this maximum entropy model to come up with the text sequence, and there we will study this beam search algorithm. Okay, so see you then.